Good morning all of you. Last 3-4 sessions we discussed about the characteristics of charge, followed with most beautiful topic called Coulombic force, the interaction between the static charges. And now don't ever think that the topic is over and we are finding few more new topics. No, the topics whatever we continue now on is the very much foundation is Coulombic force only. In fact, we will add more and more knowledge for this understanding of Coulombic force. Now, even before this Coulombic force, first PU, we know some of the forces, and most of them, if not all, most of those forces that we have come across in first PU, like the normal reaction, the tension forces. You remember we have done all such things in our laws of motion topics, right? So the forces like friction, normal reactions, tensions, or even for that matter latter it is force due to surface tensions, viscosity forces. So likewise a range of forces that we have discussed in our first PU. All these forces, remember, they come under the category of contact force. Contact means, yes, certainly two systems, two masses coming into contact with each other. Two masses coming in contact with each other, and there we are exerting or we are coming across a force. So all such forces are contact forces. And now after that, in gravitation topic also, one force, that gravitational force, is studied. Very much similar to the one which we are now talking about, the Coulombic force. Both are inverse square forces. There you have said force proportional to mass, here force depending on the charge. So these two forces, when it is there are special characteristics when it comes to the question of this Coulombic force. The same holds good even for the concept of gravitational force as well. What are those special characteristics which gives rise to an all important, a kind of central concept in physics afterwards? I call it a central concept in physics as a whole. That concept will be our topic of discussion in today's class. So very interesting and an important topic we are now going to begin with. Be ready with your books and pens. Here we start. See this small explanation. I said Q is a charge, maybe a point charge or maybe an extended charge like charged spheres, any charged objects, or it is simply a point charge. Now, as soon as I bring another charge, I write it as small q. Again, both are point charges or both are extended charges, or one extended and the other one is a point charge, any such possibility. As soon as we bring this q at a certain distance from this q, remember we are keeping it at a distance, no physical contact between them, right? Now as soon as this brought near capital Q, it will be observed this small q is affected by capital Q, either attractive or repulsive nature depending upon the nature of the charge. Now this is not in contact, you see. So that is what is the first characteristic I am writing about this as a specialty of Coulombic force, and I call this specialty as action at a distance. All happening without any physical contact between the systems, all happening at a distance, therefore I call it action at a distance. Similar is the case even with the gravitational force as well. Now the second aspect of this Coulombic force or interaction. Supposing this Q is brought near capital Q, as I said, now is there any time lag? Is there any time interval that is taken by this small q to feel that interaction is the question. You got my question? Supposing if this Q is brought near capital Q, does it take any time? Is there any time interval for this charge to experience a force? Now the answer is that it is, I don't say it is instantaneous. It does not happen all at once, but it happens too fast. In fact, the moment we are bringing the small q in near capital Q, the time interval in which it experiences is like 10 power minus 9 seconds or minus 8 seconds or minus 7 seconds. So the speed or the quickness with which the interaction is taking place is very high. Therefore, I am adding one more point as a characteristic for this Coulombic force. Action at a distance was first character, and the second one is the quickness, the speed of interaction, which is of the order of nanoseconds. Even without any contact, there is a transfer of such interaction from capital Q to small q. So these are the two specialities, and now how to understand these two specialities about this interaction. Now, to understand this speciality, Michael Faraday has given this ingenious concept of electric field. So electric field is, I will definitely call it as a very intelligent, ingenious concept. In fact, this field concept, we will introduce it as a model, but afterwards we will realize that the concept of field is a reality. In the very beginning, we will see it as a model for easier understanding, but later the field is not a model, but field will be a real entity. So let us begin with this idea. What do we mean by electric field? Any charge is surrounded by a space. Any charge is surrounded by a space in which it affects other charges. That influential space is what is referred as electric field. Right? So every charge surrounded with a space, I said. Therefore, generally whenever I said space, it's a 3D geometry. Yes, no doubt about that. But most of the times in our discussion, since we are using a plane, board which is a plane, most of the times we will be representing field in 2D geometry only, doesn't matter. So it is the space around the charge in which it affects the other charges. Now supposing here is a charge and I will have a space around the charge. Now, when again comes the question of space, the question is whether it is a finite space or infinite space. What is meant by that infinity, if at all we use in this context? We will come to that explanation soon. Now, every charge is surrounded by a space such that if I am now, according to our earlier discussion, if I am now bringing this small charge, small q, then it is, earlier it is seen as an interaction between capital Q and small q. But now our study will be converted into the interaction of the field of capital Q with the charge small q, which is present everywhere. Therefore, now we will understand both these aspects, how action at a distance is possible and also why that interaction is so, it is so quick. For both of them, what is the answer? As soon as we are bringing one more charge into this space, which we call electric field, now field interacts with this charge. So that is how the interaction between charge and charge will now be deduced to, or will be seen newly as interaction between field versus charge. So this concept of field now makes all the things easier in understanding or analyzing the electricity nature, analyzing the electric environment of a charge. Now let us see more and more characteristics and more knowledge of electric field. Now literally speaking, what is that electric field? Yes, the space of influence around a charge or system of charges. Now this is what is the literal meaning. Let us get into more and more physics part of the field now. So for now, when it is the Coulombic force between the two charges Q1 and Q2, earlier we said force between Q1 and Q2. Now onwards, what will be the modification? We will see it as the interaction of Q1 with the field produced by Q2, or interaction of Q2 due to the field produced by Q1. So the new modification is not charge versus charge, but now it is, yes, field versus charge will be our approach from now on. Now, to know more about the physics part of the electric field, here comes the most beautiful concept of representation of this electric field. Now we have, this is what is becoming the bigger topic for us. Representation of electric field in terms of both physical representation of the field and also the mathematical representation of the field, which becomes our subject matter for next 1 or 2 units as well. Now, representation of field. Now I have to represent, and that is why in the beginning I have told you we will first introduce field as a model to understand the characters. Let us use field as a model. Now for that model, where to begin with? Now here comes. See, we say every charge is surrounded by an electric field, such that now we are considering one idealization. Now supposing I have a charge and I have named it specially Q0. And what is the specialty about this charge? Means this charge also produces an electric field, but it is negligibly weak. Electric field due to Q0 will not modify, will not affect the field produced by other charges, right? So this electric field due to this charge is so negligibly small, and we don't consider such electric field due to this, and this I call it as a test charge, is our starting point. Test charge. Q0 is a test charge. When it is a charge, again question is whether it is positive charge or negative charge. Lot of positivity in our lives, therefore no negativity, no negative signs are used here. So whenever we say test charge is always test positive charge. Universal acceptance. So we should always consider test charge as a positive charge. Now using this test charge, we will now come to an important definition called line of force. Line of force. Now what do we mean by this line of force? Now imagine like this. This is some charge capital Q. Suppose it is a positive charge and a positive point charge supposing. Now in the vicinity of this Q, now I am placing this Q0, the test positive charge. I keep on telling only test charge, it means always positive. Supposing if this charge Q0 is placed near capital Q, then according to our earlier discussion, force will be experienced by this Q0. Supposing there is a constraint that this is free to move, and supposing this we consider as some fixed entity. Now because of this force, what happens? We know it is along the line joining. Therefore if you just join them, this is the direction in which it tends to move because of this electrostatic force. Therefore now it has come to this position. Here also again one more time. If you continue that, yes, this is how I keep on tracing the path that is followed by this test charge. Such imaginary path along which a test charge tends to move in an electric field is what is referred as Yes, line of force, otherwise also called field line as well. We'll be using any of these two words. So now here I define what is meant by line of force. Yes, what is that? Imaginary path along which, yes, a test charge, along which a test charge tends to move in a electric field. Now this line of force will be a tool for us to express everything regarding the electric field. Now let us see what are those things. Now let us list out all those characteristics of field lines, the lines of force. To begin with, the first one is appear to diverge from positive charge and converge towards negative charge. It is a natural consequence. Why? Because to draw the lines of force, we have taken the test charge which is positive charge. Therefore, positive always tends to move away from positive and positive always tends to move towards negative. Therefore, for this characteristic, let me show one or two simple diagrams as well. Supposing if this is what is a positive charge, if I say this is plus Q, then how to show these lines of force? Radially outwards. Radially outwards. So this is one line I have drawn, such that you will see these arrow marks are away from these things. Now similarly, other side also the same way. Right? So in any given direction, it will be the same. Now here, while representing, actually you can see that gradually I have shown a change here. More length, less length, lesser length, lesser length, like that. So what will be the meaning of that? We'll explain that as well. Right? So this is what is radially diverging rays from a positive charge. This is positive charge. And therefore, it will be the case of radially towards, that is what we mean by converge towards negative charge. So this is a field exclusively for isolated positive charge. Similarly for isolated negative charge, yes, isolated negative charge, if this is what is minus Q, all these similar ones that you earlier represented, the only thing is that these arrows will be towards. These will be towards. Therefore, this is exclusively a field of negative charge, isolated negative charge. Now, what is the case with system of charges? Supposing I have brought two charges together or three charges nearby, then what happens? Remember, here we are starting with the isolated charges where we are getting only the individual fields. In the case of two or three charged particles brought closer, then what happens? There will be modification because they start interacting with each other. Q1 interacts with Q2, Q2 interacts with Q3. Because of that interaction, what happens? The field gets modified. Now let us show one such example where we will see a modified field, otherwise called as a combined field. How is that? Let me take two charges such that this is a positive charge plus Q and this is maybe same magnitude but a negative charge. Now here earlier we have said that positive charge diverging, negative charge, positive charge diverging, negative charge converging. Therefore here these earlier the rays which we have shown radially, they modify, right? There will be distortion of lines of force. As a result, one line of course directly from plus Q to minus Q we show. The other rays See, earlier there was a line of force like this, but this line of force now gets modified. It will have a bending. So this part should be there. So this is what the field line that we get, the line of force we get. Similarly here also, yes, this is what is the line from positive to negative. From positive to negative. From positive to negative. Look at this arrow. So all such cases, whatever the rays we are showing from plus q will be diverging, and towards this minus q we see their convergence. Now the question is that this field line, they are not of q1 and they are not of q2, but these are the field lines for the combined field of this positive and the negative charge as a whole. Now similarly, what else if there is unlike charges? Now this is what we have shown for unlike charges. What will be the case for like charges? We know that the like charges, they show this repulsion. Therefore, when the charges are repelling, what is that modified field? Quite interesting, you see, plus q and suppose this is minus q. So what is that we find? We find that these rays, yes, these rays see this. The distortion is such that the magnetic field lines are also repelling one another or each other. Therefore now we get a combined field of this magnetic field like this. Like this. So this is what is the case that we have shown for a combined magnetic field of both like charges as well as unlike charges, and also for isolated charges, right? So this is one of the first characteristic that we have discussed. They appear to diverge from positive charge and converge towards negative charge. Now, second characteristic. Remember, each of the characteristics can be a 1 mark question, can be a 2 mark question, and luckily sometimes even conceptual question in our NEET CET as well. The second character, remember, the density of lines of force is a measure of, density of field lines is a measure of the strength of the field is one more point. This we use with good elegant intelligence. What is that? Density of field lines, supposing I consider a charge here which is plus q, and earlier we have seen all these field lines are, yes, diverging. They appear to diverge from this positive charge, and we know that maybe out of common observation also, more and more distance, the effect of this positive charge will decrease. We know that the effect of the charge is more nearer the charge, and the effect gradually decreases as the distance increases. Now the same can be seen in terms of our field lines. How? See, let me draw few more lines for a particular discussion. So these are all field lines that I am showing. Supposing here I consider a small area, I take a circle of a certain radius, right? The same circle, now I would like to draw at another distance. So this is at a distance r1. Now I am drawing at a distance r2, which is greater than r1. Same circle, supposing if I draw, what is that you observe? Look at this total number of field lines passing through this circle. Those two circles are of same size I have taken, do remember. Now here we will find that those number of field lines is decreasing. Now earlier we said closer to the charge, the field is stronger because it shows more effect, whereas more and more distance from the charge, its effect gradually decreases. That is what we mean by weaker field. Now here the field is stronger, and you will see that more number of field lines through a given area. This is a weaker region, weaker, I am now using the relative sense, stronger region, and this is what is weaker region, which makes the difference of the flux, it is making the difference of density of field lines. See, I am actually taking what is that meant by density? Yes, it is the number of field lines through a given area that I am taking. So more density, stronger region, less density, weaker region. Because when we represent an electric field with field lines, that representation should speak everything about that, every character and a complete nature of that particular electric field. Now similarly, in the discussion, remember, sometimes we get few examples, maybe in NEET or CET or even JEE examinations, such that, supposing here I show a charge of 8 microcoulomb, Q1 is equal to, and here I show, suppose this is a positive charge, and here I show a charge Q2 is equal to -2 microcoulomb. Supposing you have a situation like this, now when we are drawing the field lines, it is from positive charge to negative charge, a combined electric field we have shown, such that there should be a kind of small meaning that is attached. How? See, if I am drawing 1, 2, 3, because here it is 8 microcoulomb and this is 2 microcoulomb. Now this charge is in fact 4 times, yes, in magnitude it is 4 times. Q1 is 4 times of Q2. Therefore, when we are showing even the number of field lines, the 4 lines of force also should be in the same number as well. So whatever number of field lines that we show at the site of 8 microcoulomb should not be the same as this 2 microcoulomb as well. We have to show that difference, because for this characteristic not only the density but also this is another added point that you have to remember. Therefore now here what I show you is that, supposing if this is what is number 4 line I have shown, here I will show few more lines, here I will show few more lines. This is 1, 2, 3, 4, 5, 6, 7, and let me take one more, 8 lines, but here I have shown only few lines. Suppose this is 1, 2, 3, 4, 4 lines are only shown. Now 4, this is 8. In fact, here we have to show 16 lines. Therefore, I will only show 2 lines here. Now this is okay. 8 and this is only 2. This also a kind of an example for our competitive examinations. So when we are reading the question, these number of lines should be proportional to the magnitude of the charge that is shown here, like that. So the density of field lines represents the strength, more density, weaker regions, lesser density that we show. Now here you see, supposing here if I say, if this is an electric field, this is an electric field represented, then consider 2 points. I consider 2 points A and B at 2 different positions, right? Now what is that you can have your say to compare the field, which is a stronger region, which is a weaker region? Yes, A is a stronger region and B is a weaker region. This is based on this concept of density of field lines, right? Now let us come to all important third characteristic of field lines. Look at that English. Now I said the tangent drawn at a point on the line of force represents direction of field at that point. This is English part. You see, the tangent drawn at a point on the line of force, that is whenever we want to find the direction of electric field at a given point, what we need to do? Yes, we need to draw a line of force passing through that point, and a tangent drawn at that point represents the direction of the electric field. Remember, we are talking about a field which is a vector field, because remember how this field has come into existence? Yes, because of the force experienced by a test positive charge. Therefore, whatever field in the form of electric field we are representing, do remember it is a vector field. Now, this is the English part. Now, let us see what is the true meaning of that. See, earlier we said this was a charge plus Q1 and this is a charge minus Q2, and this is what we have shown. The field lines between Q1 and for the system of Q1 and minus Q2, right? Supposing this is what the field line that looks like. Arrows are very important, as I have told you. Without arrow, the field lines does not carry any meaning. Supposing at this point I want the direction of electric field, then at this point, look at this arrow mark. Depending upon that arrow mark, now I draw a tangent at that point. You know what is meant by tangents and normals. Small high school knowledge will tell you. So now I am drawing a tangent at this point. Now this tangent represents the direction of the electric field at that point. See, I am just showing it in another color, black one. So this is what is the direction of magnetic field. Supposing if it in any another point, supposing if I consider a tangent at this point, right? Tangent at this point. Now look at this tangent. This is what is the direction of electric field. What does it show? Now you will see that in this electric field, the direction of electric field is changing constantly at each and every point. The direction is not remaining the same. Now, this property which is used to find the direction of electric field by drawing tangent at that point, we can now add one more important character, which is a very regular 2 marks questions for you. Remember, it's a very regular full mark question. See, the lines of force in an electric field, whether it is due to isolated charge or whether it is due to system of charges, any electric field for that matter, this is applicable for any electric field that we are talking about. The electric field lines never intersect in a field. Field lines never, see, I am underlining this point, never intersect in the field. This is one of the characteristics. Now, it is asked for a 2 marks question. Explain, field lines never intersect in the field. Explain why they do not intersect. Now we give a kind of explanation. This is what we call proof by negation, proof by contradiction. We have to prove that they don't intersect. Therefore now we begin with if the lines intersect, suppose. Then what is that final result that we arrive at, and based on that we can now comment on the merit of the question. Now here you see, supposing lines of force intersect at a point. Suppose lines of force intersect at a point. Now at this point of intersection, use this characteristic to represent the direction. Then at the point of intersection, we can draw 2 tangents, is it not? Suppose these are what are field lines and they have intersected at a point in electric field. Then at this point of intersection, yes, you can draw 2 tangents. This is one tangent, and look here, this is another tangent. What is meant by 2 tangents? It means that at this given point, the field is acting in two different directions. Same point, same time, field acting in two different directions is just absurd. It is impossible. Therefore, field lines cannot intersect is our explanation. So this is what we do sometimes to prove by contradiction negation. Field lines never intersect in the field. What is your explanation? Yes. If they do intersect at a point, at the point of intersection we can draw two tangents, and it means that the field is acting in two different directions simultaneously, and it is not possible. Hence, field lines never intersect. So these are the four characteristics that we have shown, right? Using these four characteristics, now let us write three more important characteristics. Again, all those characteristics are very important for 1 marks or 2 marks. Let us, the first characteristic has shown that radially outwards diverging, converging this. So because of that, electric lines of force are always open curves. They are not closed curves. They are never closed curves. Second characteristic, used to verify or used to compare the strengths of the field. And third one, most important point, to find the direction of electric field. Now look at this fourth one. The fourth one, English part. The lines of force exhibit lateral repulsion, and longitudinal contraction is the characteristic that I have mentioned. What is meant by this lateral repulsion? Just now we have told that field lines, they never intersect. In fact, the field lines, they show the tendency of repelling each other. The field lines show a tendency of repelling each other, and that is what is meaning of the lateral repulsion. Now this is what is longitudinal contraction under property. That is to say that if a field of line is drawn from Q1 to Q2, suppose Q1 is positive, Q2 is negative, and we are drawing from positive to negative charge, any line of force will always tend to have minimum distance. That is, it would like to travel from that positive charge to negative charge in the shortest possible path. The tendency is always to have shortest path between the two charges. That is what is the meaning of this longitudinal contraction. Now, when we have find these 4 to 5 characteristics about field lines, now let us come to understanding of what do now we mean by uniform electric field and non-uniform electric field. See here, the uniformity is now with respect to both magnitude and direction, because we are talking about vector field. So electric field is said to be uniform if, I will write IFF, if and only if, two conditions. If the direction of field is same at every point, direction should not change at any point. So any point direction is the same. Electric field is a vector field. This uniformity, non-uniformity, when we talk about, it should be in terms of both magnitude and as well as the direction. Now what do we mean by uniform magnetic field? Uniform magnetic field, and first writing it as for two conditions. Number one, direction of field same at each and every point. See, direction of field same at each and every point. The second one is the strength of the field should also be the same at any given cross section. Same strength of the field. Same strength of the field. Now then only we can say it as the uniform. Only one of them is one of the conditions satisfied, then never it is said to be uniform electric field. Now you see, if I say the direction of field should be the same at each and every point, then certainly the only condition would be it should be having straight lines. Because for straight lines, there is no change in direction. Whenever you say a curve, Earlier we have seen curve at each and every point, the direction of tangent changes. Therefore, direction of the field same means the field lines should be straight and also parallel. You see here, parallel field lines that have represented. To show you more such number, if I draw some lines in between, yes, this is what is the electric field now I am representing. How is that? Straight, parallel, and also equidistant. Why equidistant? Because of that equidistant nature, the density of field lines will be same everywhere. Supposing now here I consider, or here I consider, or here I consider, you see here, what is that you will find? Same density of field lines everywhere, and also the direction at any given point. Now draw a tangent, it will be along that straight line, is it not? Therefore, this is said to be now a uniform electric field. And remember, 99.9%, no 100% for our board examinations or even for CET NEET examinations, we shall be using many a times only the case of uniform electric field. And this is what is a very popular representation in all our coming cases, right? Uniform. Other than this, any other representation, it will be non-uniform. Other than this, any type, then it will be non-uniform. To show you some of the non-uniform fields, earlier we have shown, remember, for isolated positive charge, what was the electric field? Yes, it was diverging or converging for negative. This is, now you will find that the direction is different at the different points, and also towards, nearer the charge, more density of field lines away from the charge, less density of field lines. Again, this, both magnitude and direction are changing, non-uniform electric field. Or else, supposing if I show an electric field like this, supposing if this is what is an electric field, here also what we find, yes, direction different at different points, and also density is different at different points, need not be straight lines. Supposing if you get like this, this is what is an electric field. This is also now a non-uniform electric field in terms of both magnitude and also direction. Direction changing at each and every point, at the same, the magnitude is also changing at each and every point, like that. Supposing I show one more example. Supposing I have a field lines like this. They are given to be equidistant, but not straight lines, but these curved lines of force. Now in such case, we will see that maybe the density of field lines is same everywhere, but the direction is keep changing. Therefore, this is also a non-uniform magnetic field. Now comes a question, what are the sources for uniform electric field and what are the sources of non-uniform magnetic field? Yes, thanks for your interest. They are the topics which we are going to continue with in our next sessions. We have all the cases where we find uniform and non-uniform. Uniform electric field, in very few cases we come across, and in most of the cases that we discuss, it will be non-uniform electric field. So this is about electric field lines and the characteristics of field lines. Remember, we have almost spent 1 hour for the understanding of why electric field and what is electric field and what are the characteristics of electric field. If you are ready with this understanding, our next session we will build the most essential buildings for this topic of electric field, because an electric field is now characterized by some vectors and some scalars. So for that electric field, what are those vectors, what are those scalars is our next coming 2 to 3 topics. Have a good day. We'll meet tomorrow with the understanding of the vectors regarding the electric field and also a scalar corresponding to electric field. Have a good day.